Hi, and welcome to this next video on OCR A-Level Chemistry. We're on Module 2.1, which is Atoms and Reactions. And in this next video, we're going to be looking at moles and gas volumes. So first thing we need to know about Avogadro's hypothesis. So let me move down a little. So we're going to look at Avogadro's hypothesis. So in 1811, I'm just going to read off the textbook. In 1811, the Italian Avogadro put forward one hypothesis, and this is now known as Avogadro's law, which stated that under the same conditions of temperature and pressure, one mole of any gas would fill the same volume of space. And now this is known as Avogadro's law. And it states that at room temperature at pressure, so at RTP, which is room temperature and pressure, one mole of any gas has a volume of 24 decimeters cubed, or in fact 24,000 centimeters cubed. And the volume per mole of gas is always equal to 24.0 dm cubed moles to the minus 1. So this is the key definition here. So molar gas volume is equal to the volume per mole of gas molecules. Volume per mole of gas molecules. And that is 24 mole to the minus 1. So at RTP, 1 mole of any gas, whether that be hydrogen or oxygen or carbon dioxide, they each have a molar volume of 24 dm cubed per mole, as any gas and 1 mole of any gas would. So to give an idea of scale, so 24 dm cubed is equivalent to the amount of air contained in 4 footballs, to give some comparison of scale. So air consists mainly of nitrogen and oxygen, which have similar relative molecular masses. Look at this, and I'll put up a diagram now. So according to that diagram, what the same volume of hydrogen would be much lighter than air, so around 2 grams according to this diagram. The mass of CO2 is much heavier than air according to this diagram. So the differences in individual particles have zero effect on the overall volume. This is because the particles, they're spread out so far, they're spread far apart, as in I'll quickly draw it to give you an idea of what I'm talking about. The particles are like that. They're like so far apart in a gas if you remember your particle theory, the gases like all of that. So these are individual gas particles and they're spread out far apart again from each other. So we can calculate amounts of gas molecules, so moles. There is an equation, what I'm trying to say is, there is an equation which links all of these together, and it's called the ideal gas equation. And it's called the ideal gas equation, but we'll come on to that in a bit. First thing is that you need to know how to convert between the amount of gas molecules, N, in moles, and the gas volume, capital V, in dm cubed or centimeter cubed. You can work out the amount in moles by dividing the volume by the molar volume. So here, if we look at, actually I want to use pink for this. So if volume V is in dm cubed, then you would do N equals, which is the number of moles, V over 24.0 moles. This is if V is in dm cubed. If volume V is in centimeter cubed, then you would need to do N equals V over 24,000 moles. This is if it's in centimeter cubed. So this is an important conversion that you need to know. I don't think they give it on the equations on the whatever they call it, the cheat sheet. I'd call it cheat sheet, kind of. They don't give this equation, so you need to memorize this. Okay, so now we have that. We're now going to look at the ideal gas equation. So gases are assumed to behave in an ideal way. So, and I'm just going to list from the textbook. So they are in continuous motion and do not experience any intermolecular forces. They exert pressure when they collide with each other and the walls of containers. All collisions between gas molecules and container walls are elastic, so they do not cause kinetic energy to be lost. The kinetic energy of gases increases with increasing temperature. The gas molecules are so small compared to the size of any container, they have found that any difference in the sizes of different gas molecules can be ignored. The relationships between the volume, pressure, temperature, and number of moles of an ideal gas can be described by this equation, the ideal gas equation. And it is PV, I'm actually going to write this in separate letters to make it more stand out. So P, V, and then the equals in black, equals N R, which I'll do in this dark green, T. So this is the ideal gas equation. Now I think this is given in the thingy, the cheat sheet that they gave you for the exam. So you don't need to memorize this, but you do need to memorize how to rearrange for certain things. You need to know how to rearrange it for certain things if you want to find a certain value. So P, so small p, and remember this ideal gas equation uses SI units, so I'm going to also write the units that each value is measured in. So P is the pressure, which is measured in pascals, and I'll put the conversions here as well. So 1 ATM equals that this many pascals, which I'm about to write, 101.325 PA. V, which is the red one, stands for volume, and volume is in cubic meters, meters cubed. So 1 meter cubed equals 10, no, equals 1,000 decimeter cubed, which is 1 million centimeter cubed. I'm not so sure. I'm not going to write the centimeter cubed because I don't remember off the top of my head. N is the number of moles. R is what we call the gas constant. And this is given in the cheat sheet as well, which is 8.314. The units are J moles to the minus 1K. So you can probably guess that T, judging by the units here, that T is the temperature measured in Kelvin. So 0 degrees Celsius equals 273 Kelvin. So this is the ideal gas equation. So it can be used to find out how the pressure and volume of gases will change as temperatures and number of moles vary. So if one thing changes, how would that affect other things? So let's do an example. I think I have a ChemCalc video on this planned. But I apparently set it for after the next video's ChemCalc. So we'll see. So this is ideal gas equation. So we'll do one word example. Actually, I think I have this in the ChemCalc video. I have a ChemCalc video planned for this. So I'll do the example in the ChemCalc video. That's coming up later. But all you need to know is you need to know what this is. We'll do one now. We'll do this simple one now. So here and one example which I'll do. Here, so the question is find, I'm just going to use the textbook one, the volume of 2 grams of O2 when heated to 50 degrees Celsius at a pressure of 1 atm, give your answer in dm cubed to 2sf. So here is our example, which I just stole from the textbook. So let's have a look at this example. So find the volume of 2 grams. Okay, so 2 grams. So let's highlight the stuff that we need. So find the volume of 2 grams of O2. So that doesn't matter. It doesn't matter what gas. This works for any gas, assuming it's an ideal gas. Of 2 grams of O2 when heated to 50 degrees Celsius at the pressure of 1 atm. So we have our information. Give your answer in dm cubed. This is also important, not meters cubed. It's dm cubed, and we need to give it to 2sf. Okay, so what do we need? So first thing I would do is I would write down what we need, what we know. So I would write down P, V, N, R, T like this in their proper forms. Okay, so as in with their proper units, as in the units that they are measured in using in the gas equation. So P, so pressure is 1 atm. We know that 1 atm is equal to, I can see up here, 101,325. So pressure is 101,325. Our volume we need to know. So that is our question mark. Our N, we can calculate N by using the N equals big M over small mr. So N equals small m over big mr, which equals 2 grams over the mr of oxygen is 32, which is equal to 0.60625 moles. So that is our N 0.0625. Alright, moles. Our R is 8.314. This is always givens. Our R is this 8.314 joules mole to the minus 1 Kelvin. And our temperature is 50 degrees Celsius. So 50 degrees Celsius plus 273. To convert from Celsius to Kelvin, you need to add 273. So 50 plus 273 is equal to 323. So 323 Kelvin. Okay, so now we plug all of those numbers into our PV with nRT. So PV equals nRT. So P is 101,325 times V equals 0.0625 times 8.314 times 323. I don't recommend doing this way. I recommend. So V is equal to 0.0625 times 8.314 times 323 all over 101,325. What you could have done is you could just rearrange this equation without putting the numbers in, and then put the numbers in. But I'm showing you to put the numbers in, and then rearrange it. And then if you put that into the calculator, that gives you V equals 1.66 times 10 to the minus 3. 1.66 times 10 to the minus 3. But this is in meters cubed. So we want the answer in decimeter cubed. So you just times that by 1,000, which will give you roughly 1 meters cubed. So V is equal to, what our answer is, 1.70 dm cubed. And this is correct to two significant figures. Okay, so that is your final answer. I will do a ChemCalc video on this, probably after I complete the moles and solutions one, because I think I accidentally put next week's ChemCalc video for the next video before this one, so I'm gonna have to think about that. Well, I might just do it in the order that there is. I might just finish off 2.1.9 and then do both ChemCalc videos. We'll see. Well, I'll see what I can do. Anyway, but there will be a ChemCalc video on ideal gas equation. Anyway, that's going to be it for this video here. Thank you all very much for watching. Hope this was useful, and I'll see you in the next video. Goodbye.